When you look up at the night sky, the stars seem fixed and motionless, but this stillness is an illusion. On the grandest scale, the universe is not just expanding, it is accelerating, pushed outward by a vast, invisible pressure. For decades, scientists assumed gravity would eventually slow this expansion. Instead, they discovered a mysterious force that dominates the cosmos, occupying the empty space between galaxies. We call this dark energy. Here on Fall Asleep with Science, we linger with puzzles like this, the quiet forces that shape everything, even when we cannot see them. If you appreciate uncovering these calm, unsettling truths about our reality, a gentle like and subscribe helps others find us. For now, settle in and let us examine the invisible engine driving the universe apart. The universe is growing. Space itself is stretching. The distances between galaxies are getting larger, not smaller, and this discovery changed everything we thought we knew about how the cosmos works. It was not always obvious. For most of human history, the night sky looked eternal, steady, and unchanging. The stars moved across the heavens and the constellations repeated their patterns year after year, making the universe appear to be a grand, infinite dome. People saw it as permanent. The idea that the entire cosmos might actually be expanding, or that galaxies could be flying apart from one another, would have sounded absurd to most early stargazers. After all, when you look up at night, it feels like everything is fixed in its place, which is why the discovery of expansion was so surprising. In the early 20th century, astronomers like Edwin Hubble looked carefully at the light from distant galaxies and noticed something subtle but extraordinary. The light was stretched, shifted toward the red end of the spectrum. This red shift meant those galaxies were not standing still. They were receding, moving away from us, and not just by chance, because the farther away a galaxy was, the faster it appeared to be retreating. The conclusion was inescapable. Space itself was expanding. Imagine a loaf of raisin bread rising in the oven. Each raisin represents a galaxy. As the dough expands, the raisins move farther apart. No single raisin is the center. Every raisin sees the others drifting away as the bread rises. That is what Hubble had found. The universe is the dough, and we are one tiny raisin among billions, carried outward by expansion. At first, scientists thought they had the picture figured out. If the universe is expanding, then perhaps it was set into motion long ago in a fiery beginning, the Big Bang, and gravity would slowly work to pull everything back together. Expansion might continue for a while, but eventually gravity should slow it and maybe even reverse it. The cosmos could collapse in what some called the Big Crunch. It sounded neat and symmetrical, and for decades, it seemed plausible. But then came the twist. In the late 1990s, two independent teams of astronomers were observing distant exploding stars called supernovae. These supernovae were like cosmic mile markers because they explode with a predictable brightness. Scientists can compare how bright they appear to us and figure out how far away they are. It is like having a set of identical light bulbs scattered around the universe. By checking how dim they look, you can tell their distance. What they found was astonishing. Those supernovae were not just far away, they were farther than they should have been if the expansion of the universe was slowing down. It was as if the galaxies were sprinting away from each other, not strolling. Expansion was not decelerating under the pull of gravity. It was accelerating, speeding up, as though some invisible hand were pushing everything apart faster and faster. This discovery was one of the biggest surprises in the history of astronomy. It won the Nobel Prize, and it gave birth to the concept we now call dark energy. The name itself tells you how little we truly know about it. It is dark because it cannot be seen, detected, or touched directly. It is energy because whatever it is, it behaves like some form of energy built into space itself, working against gravity, driving acceleration. It makes up nearly 70% of the total energy content of the universe, and yet it remains a mystery. So here we are, lying beneath the stars, knowing that nearly 3/4 of everything around us is made of something invisible, something that does not glow, does not clump, and does not behave like ordinary matter at all. When you think about that, it is humbling. All the galaxies we can see, the stars, the planets, the dust, and even the dark matter that holds galaxies together, all of it makes up only about 30% of the cosmos. The rest, the majority, is dark energy. And here is where the questions begin. What is this force? Why does it exist? How does it make the universe accelerate? Some scientists look back to Einstein for clues, long before anyone discovered cosmic acceleration. Einstein had introduced something called the cosmological constant. He added it to his equations of general relativity because he thought the universe should be static. Without it, his equations predicted expansion or contraction. By inserting this constant, he balanced things like a cosmic fudge factor. Later, when Hubble showed that the universe was indeed expanding, Einstein reportedly called the constant his biggest blunder. Yet today, that same idea looks a lot like what we call dark energy, a constant energy of space itself, woven into the very fabric of the cosmos. If empty space has energy, then expansion is not just allowed, it is inevitable. Space does not just stretch, it accelerates. Every cubic centimeter of the universe has a small but persistent amount of energy. And as the universe grows, more space means more energy, fueling further acceleration. It is a runaway effect, subtle on human scales, but overwhelming across billions of light years. You might wonder how we can be so sure about something we cannot see. The evidence comes from multiple directions. Those supernovae first pointed the way, but measurements of the cosmic microwave background, the faint afterglow of the Big Bang, also confirm it. Subtle patterns in that ancient light match a universe dominated by dark energy. Observations of galaxy clusters, gravitational lensing, and even the large-scale structure of cosmic filaments all point to the same conclusion. Something is driving expansion, and it is not ordinary matter or radiation. This is where our story really begins, with a puzzle that seems almost unfair in its scale. The universe itself is teaching us humility, whispering that the things we see are only a small fraction of reality. Dark energy does not glow, does not flicker, does not announce itself, and yet it shapes the entire fate of the cosmos. As we drift further into this journey, we will explore the theories, the experiments, and the possible destinies of a universe dominated by something we barely understand. But for now, as you settle into the rhythm of thought and breath, consider this simple but profound truth. The night sky is not just a picture of stars frozen in place. It is a living, shifting expanse carried outward by a force that no one predicted and no one can yet fully explain. And as you lie there listening, you are part of it. Every heartbeat, every breath is taking place inside this expanding universe, carried forward by invisible energy, wrapped up in a mystery that continues to unfold. When people first began to suspect that the universe might not be standing still, the idea seemed almost too bold to take seriously. For thousands of years, the sky was thought of as a kind of perfect dome, eternal and unchanging. The stars wheeled overhead each night, but the patterns they made appeared fixed. The same constellations that guided travelers in the ancient world still guide us now. To most eyes, the cosmos looked like a grand, stable backdrop against which the story of human life played out. There was comfort in that, the feeling that the heavens were permanent, steady, and unaffected by the chaos of earthly events. But curiosity has a way of nudging at those assumptions. In the early 20th century, as telescopes grew larger and more powerful, astronomers began noticing something peculiar. The faint smudges of light that speckled their photographic plates were not just stars. Some of them were entire galaxies, vast systems of billions of suns. At first, even that was hard to accept. The universe, people thought, was the Milky Way and little else. Then the realization struck that those faint smudges were far beyond our own galaxy. Suddenly, the universe became unimaginably larger, and with that enlargement came the next surprise. Those galaxies were not sitting still. They were moving. The story of this realization is often told through the name of Edwin Hubble. In the 1920s at Mount Wilson Observatory in California, Hubble and his colleagues used the most advanced telescope of their time to study galaxies. By examining the light they emitted, they could measure a shift in the wavelength. This shift is something most of us experience in daily life without even thinking about it. When a car or train speeds past with its horn blaring, the pitch drops as it moves away. That change in pitch is called the Doppler effect. Light experiences a similar effect. When a source of light moves away from us, its waves stretch, shifting toward the red end of the spectrum. It is called redshift. Hubble's measurements revealed a consistent pattern. Nearly every distant galaxy showed this redshift. The farther away it was, the greater the shift appeared. That meant the galaxies were not just drifting, they were receding, moving away from us at speeds proportional to their distance. A galaxy twice as far was moving away twice as fast. The universe was expanding in every direction like a balloon inflating. The image of a balloon often comes up here, and it is useful. Imagine dots drawn on the surface of a balloon. As you blow air into it, the dots spread apart. None of them are the center of the expansion. Each one sees all the others moving away. That is what our universe is like. From our perspective here on Earth, it might feel as if we are at the center, because everywhere we look, galaxies recede. But from the viewpoint of any other galaxy, the same would be true. Expansion is not about galaxies racing through space. It is about space itself stretching, carrying them with it. At first, this discovery was astonishing enough on its own. It overturned the static, eternal universe that people had assumed for millennia. Instead of a cosmos that always was and always would be, the picture emerged of a universe with a history, one that had once been smaller and denser. If expansion was happening now, then, in the past, everything must have been closer together, compressed into a much more compact state. Follow that thought far enough back, and you arrive at the idea of the Big Bang, a cosmic beginning. Not everyone was ready to accept this at first. Even Einstein, whose theory of general relativity provided the mathematics that allowed such a universe to be imagined, initially resisted the idea. He had believed in a static cosmos and had added his cosmological constant to keep it that way. When Hubble's evidence for expansion became undeniable, Einstein reportedly visited Mount Wilson and looked through the telescope himself. According to accounts, he admitted that abandoning the constant might have been the wiser choice. He called introducing it his greatest mistake. although later physics would bring it back in an entirely new light. The expansion was not just a curiosity. It changed how scientists thought about almost everything in cosmology. If the universe had a beginning, then it had an age. If it was expanding, then there was a future to consider, a fate shaped by the push of expansion and the pull of gravity. For the first time, human beings could place themselves inside a dynamic story of the cosmos, one with a past, a present, and an unfolding future. Still in those early decades, the expectation was that gravity, the great force pulling matter together, would gradually slow expansion. Perhaps the universe would keep expanding forever, but at an ever-decreasing rate. Or maybe it would eventually halt in reverse, collapsing into a big crunch. Both possibilities seemed reasonable, and scientists debated them. What no one suspected was that expansion itself could speed up. That idea simply was not on the table. The universe was expanding, yes, but gravity was always the counterbalance. Until decades later, the measurements of distant supernovae would reveal something startling. But let us linger for a while in the time before that revelation, when expansion itself was still the great surprise. The idea that galaxies were moving apart at immense speeds had to be absorbed slowly. For the public, it trickled in through newspapers and magazines, often presented with dramatic imagery. For scientists, it became the foundation of modern cosmology. The universe was not static wallpaper. It was dynamic, alive in its way, swelling outward with each passing moment. Think about what that means for the night sky. You see, the stars above are part of the Milky Way, bound together by gravity. They will not drift apart anytime soon. But the faint smudges beyond the Andromeda Galaxy, the spirals and ellipticals visible only with telescopes, those are part of the grand outward rush. Billions of galaxies, each filled with billions of stars, all being carried apart by expansion. The scale is hard to grasp. Distances are measured not in miles, but in millions and billions of light years. And over those scales, expansion is not a gentle drift, but a profound reshaping of the cosmos itself. Even so, we do not feel it locally. Your room, your city, even our solar system are all held together by forces far stronger than cosmic expansion. Gravity binds Earth to the sun to the Milky Way. Expansion only becomes noticeable when you look across the vast gulfs between galaxies. It is on those scales that the stretching of space reveals itself. Silent, steady, unstoppable. Astronomers began to calculate rates. The Hubble constant, as it became known, describes how fast expansion proceeds for each unit of distance. Debate swirled around its exact value, a debate that continues even now with modern satellites and observatories. But regardless of the number, the principle was clear. The universe was not static. It was changing. The distance between galaxies was not fixed. It was growing. And so the stage was set for one of the greatest scientific surprises of the 20th century. What began as a discovery about redshift in galaxies turned into a complete reimagining of the cosmos. From a seemingly eternal dome of stars, the universe became a story with a beginning, an evolution, and a destiny. It became a place where the very fabric of space could stretch and grow, where time and distance were linked in ways our everyday experience could never suggest. The wonder of it is not just in the equations or the measurements, but in the perspective it gives. Every glance at the night sky now carries with it the knowledge that those pinpricks of light are set against a backdrop that is itself in motion. The cosmos is not a stage on which things happen. The cosmos is itself an actor, dynamic and restless. Expansion is its gesture, subtle in the short span of human lifetimes, but vast and undeniable across billions of years. As you listen and settle deeper into this quiet reflection, imagine that balloon once more, not as a toy in your hand, but as the very fabric of reality. Imagine the galaxies as raisins, yes, but also as islands of light, each one a home to uncountable stars. And imagine that all of it is being carried outward away from each other by a process that began long before you were born and will continue long after. That is the strange discovery that changed everything. And it is the doorway into the deeper puzzle of why the expansion is not slowing but speeding up. When you picture empty space, it is natural to imagine a true nothing, a vast black vacuum, cold and silent, with nothing at all inside it. For centuries, that was the idea. Space was the backdrop, the blank canvas on which planets and stars were arranged. It was thought of as pure emptiness, an infinite void without structure or content. The stars and galaxies were the real things, and the space between them was simply the absence of anything. But as science began to dig deeper, that image of emptiness started to unravel. What we call empty space turns out not to be empty at all. It has properties, behavior, and even energy. The void is not void. It is a kind of stage that participates in the play of the universe rather than simply holding it. This realization has become central to understanding why the universe expands the way it does and why acceleration, strange as it seems, might actually be built into the nature of space itself. To start, think about how we know that space has structure. One clue comes from quantum mechanics, that branch of physics that deals with the very small. In quantum theory, there is no true nothingness. Even in a region stripped of particles and radiation, quantum fields remain. These fields are like invisible fabric stretched across all of reality. They can never be completely quiet. They flicker with constant activity, tiny fluctuations that pop in and out of existence. This restless undercurrent is sometimes called vacuum energy. The phrase vacuum energy sounds contradictory. A vacuum should be empty, yet here is energy embedded in it. To make sense of it, imagine a perfectly still pond. From a distance, it might appear flat, motionless, almost featureless. But when you look closer, you notice tiny ripples, molecules vibrating, currents swirling. Even in stillness, activity is present. The quantum vacuum is similar. It looks empty, but at microscopic scales, it teems with virtual particles, fleeting ripples of energy that appear and vanish in unimaginably short timescales. Physicists first realized this was not just speculation when they began to notice real effects caused by vacuum fluctuations. One famous example is the Casimir effect. If you place two metal plates very close together in a vacuum, strange things happen. The quantum fluctuations outside the plates are slightly different from those between them. This imbalance produces a measurable force that pushes the plates together even though no particles or light are present. It is as if the vacuum itself is exerting a pressure. Experiments have confirmed this effect. What seems like emptiness is alive with activity. Now, if empty space has energy, then it can influence the universe on larger scales. General relativity, Einstein's theory of gravity, teaches us that energy and matter tell space how to curve. Normally, we think of matter like stars or planets, creating that curvature. But if space itself carries energy, then it too can shape the universe. And because this vacuum energy has a very strange property, negative pressure, it can act not to pull things together, but to push them apart. This is where the story of cosmic acceleration begins to connect with the idea of an active vacuum. When those supernova observations showed that expansion was speeding up, one natural explanation was that empty space itself had energy built into it. The more space there is, the more total vacuum energy exists. And that energy drives expansion even faster. Instead of the universe slowing under the pull of gravity, it accelerates because space itself pushes outward. This brings us back to one of the most intriguing chapters in the history of physics, Einstein's cosmological constant. When Einstein first developed his general theory of relativity in 1915, he had created one of the most beautiful and powerful ideas in science. It described gravity not as an invisible force reaching across space, but as the bending of space itself. Matter told space how to curve, and curved space told matter how to move. Suddenly, the motions of planets, the fall of objects, and even the bending of light could all be explained by the same elegant framework. But with elegance came a puzzle. Einstein's equations predicted that the universe could not be static. The mathematics suggested that space itself should either be expanding or contracting, pulled by the collective gravity of everything inside it. To Einstein, this seemed unacceptable. For centuries, the dominant belief was that the cosmos was eternal and unchanging on the larger scales. Stars might live and die, but the universe as a whole was thought to be steady. Einstein trusted his mathematics, but he also trusted that centuries of assumptions could not all be wrong. So, he added a term to his equations, a balancing factor he called the cosmological constant. This constant acted like a kind of repulsive force, counteracting the pull of gravity on large scales and holding the universe in a steady state. With it, the equations allowed for a cosmos that neither collapsed nor expanded. Without it, the universe was doomed to change. The constant became a mathematical patch, an adjustment made not because of evidence, but because of expectation. But the story did not end there. In the 1920s, when Edwin Hubble's observations revealed that the universe was indeed expanding, Einstein reportedly admitted that his cosmological constant had been unnecessary. He called introducing it his greatest blunder. He regretted the choice, believing it had distracted from the truth his own mathematics had already revealed. And yet, history has a way of circling back. When astronomers in the late 20th century discovered that the universe's expansion was accelerating, they needed an explanation. Gravity alone could not account for it. Something was acting against gravity, something with a repulsive effect on cosmic scales. The simplest way to describe it was to reintroduce the cosmological constant. Einstein's blunder, it seemed, might have been insight ahead of its time. To understand why the constant matters, it helps to look at what it represents. In the equations of relativity, it acts like an intrinsic energy of space itself. Unlike ordinary matter or radiation, which dilute as the universe expands, the constant remains the same everywhere. A cubic meter of space always carries the same amount of this energy, no matter how large the universe becomes. That means as expansion creates more space, the total amount of this energy increases, fueling acceleration. In a way, the cosmological constant is the mathematical embodiment of the idea that empty space is not empty. It is the simplest possible form of dark energy, unchanging, uniform, always present. It simply exists as a property of the vacuum itself. However, a deep puzzle remains. Quantum physics can estimate the amount of energy that should be present in empty space. When physicists make those calculations, the number is staggering. It comes out about 120 orders of magnitude larger than the dark energy we actually observe. That means the predicted value is a 1 followed by 120 zeros times greater than what the cosmos reveals. This mismatch is sometimes called the worst theoretical prediction in physics. Something is clearly missing in our understanding. Either we are miscalculating or something cancels out most of that energy, leaving behind only a faint residue that drives acceleration. This mystery lies at the heart of modern cosmology. We know empty space carries energy. We know that energy accelerates expansion, but we do not know why the amount is what it is. Why not far larger? Why not zero? Why precisely this tiny but significant value? It is one of the deepest questions science faces, and it remains unresolved. Still, even with the mystery unsolved, the evidence is overwhelming that the vacuum is active. This changes how we think about the universe entirely. The cosmos is not a collection of objects floating in an empty container. It is a fabric in which even the container itself participates. Expansion is not galaxies rushing outward into nothing. It is space itself stretching, powered by its own hidden energy. This realization can feel unsettling, but it can also be strangely comforting. It means that the universe is richer than it appears, layered with activity, even in its most silent corners. What looks like nothing may be the most powerful something of all, quietly shaping the destiny of everything. And if you pause for a moment, letting that sink in, you might notice how it reframes the night sky. Those dark gaps between the stars, those vast gulfs between galaxies, are not voids in the way we once imagined. They are full of this invisible presence. They are where the mystery of dark energy lives. Every patch of black sky you have ever stared into is humming with the energy of the vacuum, patient, persistent, unstoppable. As science continues to probe, new questions branch out. Could vacuum energy vary over time? Could it change its strength as the universe evolves? Some theories suggest it might not be a constant at all, but something dynamic, sometimes called quintessence. In those ideas, empty space carries a field that slowly shifts, altering expansion gradually. Others argue that what we call dark energy may be a hint of new physics beyond both relativity and quantum theory. Perhaps our picture of gravity itself needs revision. For now, though, the simplest explanation remains that empty space has energy, and that this energy drives acceleration. A simple idea with profound consequences. The emptiness that is not empty may be the reason galaxies will eventually drift so far apart that they slip beyond one another's view. It may determine whether the universe expands forever, grows cold and dark, or faces stranger destinies still. And while those outcomes lie far in the future, the principle is here now in every moment. Even in the quietest vacuum a particle accelerator can create, even in the darkness between stars, the universe is alive with hidden energy, not the kind we can harness for power plants or light bulbs, but the kind that shapes the entire story of cosmic evolution. The realization that nothing is not nothing has become one of the most astonishing shifts in human thought. It reminds us that our intuitions shaped on earthly scales cannot always be trusted in the realm of the very small or the very large. Emptiness feels like absence. In reality, emptiness is presence of the strangest kind. As you listen, perhaps letting your own thoughts wander like galaxies carried by expansion, you are surrounded by this active vacuum. It is not something separate from you. You are part of it. Every atom in your body, every space between those atoms is immersed in quantum fields. You are both matter and emptiness woven together by physics that remains only partly understood. And that, in its quiet way, is as wondrous as anything we will encounter on this journey. The cosmological constant, born as a patch, abandoned as a blunder, and revived as a cornerstone, continues to shape our understanding of the universe. It tells us that even the emptiest vacuum is alive with energy. It tells us that acceleration is not a quirk, but perhaps the natural destiny of a cosmos filled with space that refuses to stay still. When Edwin Hubble stood at the eyepiece of the Hooker telescope on Mount Wilson in the 1920s, he probably did not imagine he was about to upend our understanding of the universe. The telescope itself was the largest in the world at the time, a 100-inch mirror-gathering light from distant objects so faint they had only recently been recognized as separate from the stars of the Milky Way. Until then, many astronomers believed the Milky Way was the whole universe. Those spiral smudges photographed on long exposures were thought by some to be little more than nebulous clouds within our galaxy, but careful measurements were beginning to suggest otherwise. They were too far, too large, and too distinct to belong to our own system. They were entire galaxies of their own, scattered far beyond the boundaries of the Milky Way. Hubble's task was to measure them more precisely. He used a type of star called a Cepheid variable. These stars pulse in brightness at a regular rhythm, and their period of pulsing is directly related to their intrinsic luminosity. By comparing how bright they look to how bright they truly are, astronomers can measure their distance. It was like discovering cosmic lighthouses with built-in yardsticks. When Hubble applied this method, the results were staggering. The Andromeda Spiral, previously thought to be just a hazy patch nearby, was actually 2.5 million light-years away. Other nebulae, the ones scattered across photographic plates, turned out to be even farther. The universe was not just the Milky Way. It was filled with galaxies, each with billions of stars stretching out in every direction. Even that discovery alone would have been enough to change the course of astronomy. But Hubble did not stop there. He compared these distances to the spectra of galaxies, the detailed fingerprints of their light. Many of them showed redshift, a stretching of light waves toward the red end of the spectrum. The pattern was undeniable. The farther away a galaxy was, the greater its redshift appeared, and redshift meant motion. These galaxies were receding, moving away from us as if carried on a tide that no one had seen before. Hubble published his results in 1929, and they spread quickly through the scientific world. The relationship he described is now called Hubble's law. The recessional velocity of a galaxy is proportional to its distance. Double the distance, double the speed. It was a simple linear pattern, but its implications were anything but simple. It meant the universe was expanding, space itself was stretching, and every galaxy not gravitationally bound to its neighbors was being carried away. This was the surprise that changed cosmology. Until that moment, many scientists, Einstein included, clung to the picture of a static universe. Hubble's observations made that impossible. The cosmos was dynamic, in motion, evolving. The light from galaxies was not just telling us where they were, but how the fabric of reality itself was behaving. It is hard to appreciate from our perspective nearly a century later just how shocking this must have felt. Imagine thinking of the universe as a grand, eternal stage, only to learn that the stage itself is swelling, stretching, and growing larger with every moment. For centuries, human thought had placed Earth at the center, then the Sun, then the Milky Way. Now, even the galaxy was just one of countless others, all adrift in an expanding sea. The scale of it was overwhelming, but also profoundly humbling. The discovery soon connected with the mathematics of general relativity. Einstein's equations naturally predicted expansion. Hubble's results seemed to confirm what the equations had been hinting at all along. The universe had a past, and therefore, perhaps a beginning. This realization gave rise to the concept of the Big Bang. If galaxies were moving apart now, then in the distant past they must have been closer. Trace the expansion backward, and you arrive at a moment when everything was compressed into an incredibly hot, dense state. That idea was controversial at first, but it grew stronger with time as more evidence accumulated. Hubble's contribution was the spark. Without his surprise, the Big Bang might have remained a mathematical curiosity rather than a central framework of modern cosmology. Even today, astronomers continue to measure the Hubble constant, the rate at which the universe expands per unit of distance. Different methods give slightly different values, leading to a disagreement known as the Hubble tension. Some believe it points to hidden systematics in the data, while others suspect it might be a clue to new physics. In a way, Hubble's surprise continues to surprise us still. The image of galaxies on the run captures the imagination. We tend to think of motion in terms of objects moving through space, like cars on a road. But galaxies are not racing through a fixed background. The space between them stretches, carrying them apart locally. Gravity holds systems together. The Andromeda Galaxy, for example, is on a collision course with the Milky Way despite cosmic expansion. But on the grand scale of clusters and superclusters, the general motion is outward, a relentless drift into larger separations. This has consequences for what the universe will look like in the far future. As expansion continues, distant galaxies will move farther and farther away. Their light will become increasingly redshifted, stretched into wavelengths too long for our instruments to detect. Eventually, only the nearest galaxies, bound to our own will, remain visible. To future astronomers, billions of years from now, the universe may appear emptier, lonelier, stripped of the evidence we now see so clearly. Once the surprise of cosmic expansion settled in, scientists naturally began to wonder what would happen next. If galaxies were moving apart, would they continue to do so forever, or would something eventually slow them down? The obvious candidate was gravity. For all of human history, gravity had been the reliable anchor that kept our feet on the ground, the moon in its orbit, and planets circling the sun. It was the quiet but unyielding pull that bound everything together. On cosmic scales, it was the dominant force shaping galaxies, stars, and clusters. If anything could halt the outward rush of the universe, it would be gravity. The way to picture it is simple. Imagine tossing a ball upward. The ball leaves your hand with speed, but gravity works against it. If the throw is weak, the ball rises a little and falls back. If the throw is stronger, the ball climbs higher before gravity still pulls it back down. Only if the throw reaches a certain escape velocity does the ball break free of Earth's pull. The universe seemed like a grand version of this same story. Expansion was the toss, gravity the pull. The ultimate fate would depend on which one had the greater hand. To explore this, cosmologists frame the question in terms of density. The more matter the universe contains, the more gravity it generates. A dense cosmos would have strong enough gravity to slow expansion and perhaps reverse it. A sparse cosmos with little matter would not. Expansion would continue forever, only gently decelerating. Somewhere between those extremes lay a critical density, a precise balance where expansion would slow but never quite halt. The search for that critical balance became one of the guiding quests of 20th century cosmology, observations began to shape the possibilities. Galaxies are massive, but they are not enough on their own. Even when astronomers counted all visible matter, it fell far short of the critical density. This was the origin of the hunt for dark matter. Unseen mass inferred from the way galaxies rotate and clusters hold together. If dark matter was real, perhaps it supplied the missing density. Perhaps the universe was still heavy enough for gravity to win. For decades, the debate continued between a closed universe that would collapse and an open universe that would expand forever. For a long while, the assumption was that gravity must at least be slowing expansion. Even if the universe was too sparse to collapse, surely gravity was tugging against the outward motion. It seemed impossible that expansion could speed up. That would require something entirely new, something pushing outward with greater force than gravity's pull. Few imagined such a thing. The mental picture was still the ball tossed upward, always decelerating, even if it never returned. And then in the late 1990s came the shock. Teams studying distant supernovae found that faraway galaxies were not slowing down. They were receding faster than expected. Expansion was accelerating. The tug of war had been decided, but not in the way anyone had predicted. Gravity was not only losing, it was being overwhelmed by something stronger, something no one had accounted for. That something became known as dark energy. Even so, gravity remains half the story. Without it, there would be no stars, no galaxies, no planets, no people to wonder about cosmic acceleration. The universe would be nothing more than a thin soup of particles stretched too quickly to clump. Gravity shapes the local, binding matter together into luminous structures. Expansion shapes the global, carrying those structures apart on ever-widening scales. The balance between them is what gives the universe its character. To see this balance, you only have to consider our own galaxy. The Milky Way is bound together by gravity. Stars orbit its center, locked into paths determined by the combined pull of visible and dark matter. Expansion does not tear the galaxy apart. On these scales, gravity wins easily. Even nearby, Andromeda is not receding. Its mutual attraction with the Milky Way is strong enough to overcome expansion. The two galaxies are on a slow-motion collision course set to merge billions of years from now. Clusters of galaxies too remain gravitationally bound. Expansion cannot pry them apart, but beyond those scales, the stretching of space dominates. Superclusters drift away from one another, and no amount of gravity is strong enough to reel them back in. It is this layered balance that makes the universe such a rich structure. Within galaxies and clusters, gravity rules. Between them, expansion reigns. One is a pull, the other a stretch. Together they create a cosmos that is both cohesive and restless. Without expansion, gravity would eventually drag everything into one massive collapse. Without gravity, expansion would scatter matter so evenly that no stars or galaxies would ever form. Only together do they give rise to the universe we see. For scientists, the cosmic tug-of-war is not just a metaphor. It is described in equations, tested through observations, and mapped through simulations. But for the rest of us, it is also a reminder of balance at the largest possible scale. The universe itself is a contest of opposites, played out not in minutes or centuries, but in billions of years. It is a contest that produced the galaxies, the stars, and eventually the conditions for life to exist. The discovery that expansion is winning in an accelerating fashion does not erase gravity's role. It only reframes it. Gravity still shapes the local, but on the larger scales, expansion fueled by dark energy dominates. The tug of war is no longer even. It has become a game where one side grows stronger with time while the other remains constant. Every new cubic light-year of space adds more of the repulsive energy while gravity's influence weakens with distance. The outcome, at least for now, is clear. Expansion will continue to accelerate. Still, the details remain uncertain. How exactly does dark energy behave? Is it truly a constant? Or could it vary? Could gravity itself behave differently on the larger scales than we expect? These questions keep the contest alive in scientific debate. From the perspective of someone lying under the night sky, though, the simplicity remains. The stars overhead are bound together by gravity, safe from expansion's pull. Yet the darkness between galaxies is filled with an invisible energy that drives them farther apart. Both forces act at once, silently, steadily, creating the cosmos we inhabit. The universe is not governed by a single hand, but by the interplay of two, each essential, each shaping the grand design. In the late 20th century, cosmology was a field full of questions, but many scientists believed they had a broad sense of where things were headed. The universe was expanding. As Hubble had shown decades earlier, gravity was tugging against that expansion, and the debate centered on how strong that tug was. Did the universe have enough matter to one day stop expansion and reverse it, collapsing into a big crunch? Or was it too sparse, destined to expand forever, slowly decelerating but never halting? For many, those seemed to be the only two options. What came next would prove both shocking and unsettling, rewriting that picture entirely. The key to the discovery came from an unusual kind of star. When massive stars reach the ends of their lives, some explode as supernovae. These explosions are not only dramatic, they are extraordinarily bright, outshining entire galaxies for a brief time. Among them, one particular type called Type Ia supernovae holds special importance. These events occur when a white dwarf star in a binary system accumulates matter from its companion until it reaches a critical mass and detonates. Because this process always triggers at nearly the same threshold, the explosions are remarkably uniform in brightness. They act like cosmic beacons or standard candles scattered throughout the universe. By comparing their known luminosity to how bright they appear from Earth, astronomers can measure distances with great precision. In the 1990s, two teams of scientists set out to use these stellar explosions as markers to map the expansion of the universe. One was the Supernova Cosmology Project, based primarily in the United States. The other was the High Z Supernova Search Team, a more international collaboration. Their goal was to find distant Type Ia supernovae, measure their brightness, and determine how quickly the universe had been expanding in the past compared to the present. If gravity was slowing expansion, then distant galaxies whose light had been traveling for billions of years should reveal a faster expansion in the past than we see today. The supernovae would act as time machines, giving a glimpse into how the cosmos had behaved across deep stretches of history. The work was painstaking. Detecting supernovae at such distances required scanning wide areas of the sky, then carefully tracking faint smudges of light as they brightened and faded. Each candidate had to be confirmed spectroscopically, its type identified, and its redshift measured. Teams coordinated across observatories, continents, and time zones, chasing these brief cosmic explosions before they disappeared. The process demanded not just technical expertise, but extraordinary persistence. When the results began to come in, they were baffling. The distant supernovae did not appear as bright as expected. At their redshifts, If expansion had been slowing under the pull of gravity, the explosions should have been somewhat brighter, closer to us than they appeared to be. Instead, they looked dimmer, farther away. The only consistent explanation was that expansion had not slowed. It had sped up. The universe was not decelerating. It was accelerating. For the scientists involved, this was almost unbelievable. The assumption that gravity was the dominant influence had been so deeply ingrained that the idea of acceleration felt almost absurd. Some suspected errors in calibration, perhaps dust obscuring the supernovae, making them appear dimmer than they really were. Others wondered about biases in selection, statistical flukes, or misclassified events. But as the data accumulated from both teams independently, the pattern held. The universe's expansion was accelerating. The implications were profound. Some new component of the cosmos, something previously unrecognized, had to be driving this acceleration. It was not ordinary matter or radiation. It was not dark matter, which pulls inward rather than pushes outward. It had to be something else, a form of energy embedded in space itself. Scientists gave it a name that conveyed both its mystery and its role: dark energy. In 1998, the announcement shook the scientific world. Decades of assumptions had been overturned. The universe was not slowing down on its way to one of two possible fates. It was racing outward faster and faster, driven by a force that no one had seen before. What had begun as careful measurements of distant starlight ended as one of the most surprising discoveries in modern physics. The two teams later shared the Nobel Prize in Physics for their work, but recognition was only part of the story. The deeper impact was the opening of an entirely new chapter in cosmology. Instead of a universe controlled by gravity and matter alone, we now had to reckon with an additional ingredient, and not a small one. Dark energy, by the best estimates, accounts for nearly 70% of the total energy of the universe. Matter, both ordinary and dark, makes up less than a third. What we see in stars, planets, and gas is just a thin slice of reality. This revelation reframed almost every question about the cosmos. What is the fate of a universe dominated by dark energy? How does it interact with matter and radiation? Is it truly constant, or does it change over time? Could it be connected to the vacuum energy predicted by quantum mechanics? Or is it something entirely different? For the scientists of the 1990s, the initial reaction was a mix of shock, skepticism, and exhilaration. The data had forced them to accept something they had not been looking for. Often in science, the greatest discoveries come not from confirming expectations, but from stumbling upon what no one had imagined. The faint light of distant, exploding stars had revealed a universe stranger than anticipated. Over the following years, other lines of evidence supported the finding. Measurements of the cosmic microwave background showed patterns consistent with a universe dominated by dark energy. Large-scale surveys of galaxy distributions confirmed the same picture. Slowly, the acceleration discovered in 1998 became not just an anomaly, but a cornerstone of modern cosmology. It is worth pausing on the human dimension of this story. Picture the astronomers in the mid-90s spending long nights at telescopes, poring over data, double-checking every possible source of error. To be part of a discovery that rewrote the cosmic story was both exhilarating and daunting. Some have spoken about the disbelief they felt when the data refused to line up with expectations, the long discussions in conference rooms, the moments of realization that they were glimpsing something extraordinary. The supernovae themselves, in a way, became teachers. These brief, violent deaths of stars scattered across billions of light years were like messengers from the deep past. They carried news not just of their own explosions, but of the expansion of the universe itself. Each dimming light was a reminder that the cosmos is not simply drifting outward under inertia. It is being pushed, urged forward by something embedded in the very fabric of reality. Today, the discovery of acceleration stands as one of the great turning points in our understanding of the universe. It did not close the story. It opened it wider. Dark energy remains mysterious, its nature still unknown. But the revelation of 1998 ensured that no model of cosmology can ignore it. The tug of war between gravity and expansion turned out to have a third participant, invisible yet dominant, shifting the balance in ways no one had foreseen. And so, as you imagine the night sky filled with galaxies, each containing billions of stars, remember that they are not merely drifting apart under the fading echo of the Big Bang. They are accelerating away, carried by a force that remains one of the deepest puzzles in science. The light of distant supernovae told us this patiently, quietly, across billions of years. It was up to us to notice. The discovery of cosmic acceleration in 1998 left astronomers and physicists staring at a mystery with no clear name. The data was unambiguous. Expansion was speeding up. But what could cause such a thing? Nothing in the familiar catalog of cosmic ingredients seemed adequate. Matter pulled, radiation pulled. There was no known source of a cosmic push, and yet the evidence was undeniable. Something had to be there. When scientists first tried to make sense of this, they reached for the simplest explanation available: Einstein's cosmological constant. Once discarded as a blunder, it offered a ready-made mathematical framework. It represented an intrinsic energy of space itself, uniform and unchanging, with negative pressure that would naturally accelerate expansion. By reintroducing the constant into the equations of relativity, the data could be explained. Expansion was driven not by matter, but by the vacuum. This did not mean everyone was satisfied. The cosmological constant raised difficult questions. Why was its value so small compared to quantum predictions? Why was it not zero? Why did it take this particular magnitude just large enough to drive acceleration now but not earlier in cosmic history? These puzzles made many physicists uneasy. Still, as a first step, the constant was a way to make sense of the shocking observations. Gradually, the term dark energy emerged as a broader label. It was a way of naming the unknown without prematurely locking into one specific explanation. Dark matter had already entered the lexicon decades earlier to describe unseen mass inferred from galaxy rotations. Dark energy extended the pattern, a placeholder name for an unseen component, inferred only through its gravitational effects. The dark did not mean sinister. It meant hidden, mysterious, not directly observable with existing instruments. The birth of this idea was not a single moment, but a gradual crystallization. As more teams checked and rechecked the supernova data, and as large-scale surveys confirmed the picture, the community coalesced around the concept. Something beyond matter and radiation existed, something filling space, smooth and pervasive, shaping the cosmos on its larger scales. Dark energy was not defined in detail. It was a category, a recognition that the equations of cosmology needed an additional term. Some scientists embraced the cosmological constant as the simplest form of dark energy. Others explored more exotic ideas, scalar fields that could vary over time, new forces acting on cosmic scales, or modifications to gravity itself. But the unifying thread was that the universe could no longer be described without this invisible component. By the early 2000s, dark energy had become a standard part of cosmological discussions. The Lambda CDM model, where lambda represents the cosmological constant and CDM stands for cold, dark matter, rose to prominence as the simplest framework matching observations. In this model, about 70% of the universe's energy comes from dark energy, about 25% from dark matter, and only about 5% from ordinary matter. This hierarchy was startling. Everything familiar, stars, planets, gas, dust, even ourselves, made up just a sliver of the cosmic budget. The dominant component was something we could not see, could not touch, and did not understand. The birth of dark energy as an idea was also the birth of new questions. How can we measure it more precisely? How can we distinguish between a true cosmological constant and something more dynamic? What role did it play in the earliest moments of the universe? And what role will it play in the far future? These questions spurred new missions, new telescopes, and new collaborations. The timing of the discovery added another layer of curiosity. Cosmic acceleration seemed to become significant only in the relatively recent universe, billions of years after the Big Bang. Before that, matter and radiation dominated, pulling galaxies together, slowing expansion. Only later did dark energy emerge as the leading influence. Why now? This so-called coincidence problem puzzled theorists. Was it really chance that we lived at the epoch when dark energy became important? Or did it point to something deeper about the structure of physical laws? As with many great ideas in science, the birth of dark energy was not the end of a journey, but the start of one. It framed a new landscape of research, one where the larger scales of the cosmos and the smaller scales of quantum theory seemed to intersect. It brought Einstein's equations back into conversation with the mysteries of the vacuum, reminding physicists that the universe often keeps its secrets in plain sight until the right evidence forces us to confront them. And so dark energy entered the lexicon not as a solved concept, but as a working placeholder, an acknowledgement of our ignorance as much as our progress. It remains today one of the central mysteries in science, a force that defines the destiny of the cosmos while eluding clear explanation. Its birth as an idea was not dramatic, not a single flash of insight, but a collective recognition slowly realized that the universe is stranger and richer than we had thought. The night sky has always inspired questions. In the late 20th century, those questions gained a new dimension. Not only do galaxies move apart, but they accelerate. Not only is the cosmos vast, but it is dominated by an invisible energy we do not understand. Dark energy was born as an idea in response to this evidence, a reminder that the universe is always one step ahead of us, offering puzzles that stretch our imagination as much as our mathematics. And even now, as you picture galaxies receding into the darkness, you can imagine them carried not just by inertia, but by this hidden presence, this pervasive energy woven into every cubic centimeter of space. It does not shine, it does not cluster, but it defines the rhythm of expansion itself. The concept may have been born in conference rooms and observatories out of charts and equations, but its reality is written across the cosmos. Every galaxy drifting outward is a signpost pointing to it. Dark energy as an idea was born not because we imagined it, but because the universe left us no choice but to name what we did not yet know. The phrase "nothing has energy" sounds contradictory at first. By definition, nothing should be emptiness, absence, a void without particles or radiation. For centuries, that was the intuition. The vacuum was viewed as a passive backdrop, a stage on which the actors of matter and light performed. Yet, modern physics has forced us to reconsider that intuition. In the strange language of quantum mechanics, even nothing is restless. The vacuum is not truly empty. It is alive with activity. To understand this, we must step into the world of quantum fields. In our everyday sense, we think of particles like electrons and photons as the basic building blocks of nature. But in quantum field theory, particles are not fundamental objects in themselves. They are excitations or ripples of underlying fields that permeate all of space. The electron field exists everywhere, and electrons are merely disturbances within it. Because of the uncertainty principle in quantum mechanics, these fields can never be completely still. They fluctuate, jittering with tiny amounts of energy even in their lowest states. What we call the vacuum is actually a seething foam of virtual particles flickering into and out of existence, borrowing energy briefly before annihilating back into the void. This background buzz is called zero-point energy. At human scales, this effect is invisible. You cannot notice vacuum energy when you turn off the lights in a room. But in delicate experiments, traces of it emerge. One of the most famous examples is the Casimir effect. If you place two uncharged metal plates extremely close together in a vacuum, they experience a mysterious, attractive force. The explanation lies in the quantum fluctuations of the electromagnetic field. Because the gap between the plates is so small, certain wavelengths of fluctuations do not fit inside, while outside the plates, all wavelengths are allowed. This creates a pressure difference. The plates are nudged together by the restless vacuum itself. It is a small force, detectable only with sensitive instruments, but it proves a profound point. Nothingness has consequences. Physicists naturally wondered whether this vacuum energy might be the source of dark energy. If space itself carries energy, perhaps that is what drives cosmic acceleration. The logic seems straightforward. As the universe expands, more vacuum is created. And if that vacuum has repulsive pressure, it pushes the universe apart faster. The idea ties together quantum field theory and cosmology in a tantalizing way. However, when theorists calculate the expected amount of vacuum energy, the numbers present a massive problem. Depending on the details, estimates from quantum theory come out up to 120 orders of magnitude larger than the observed value of dark energy. That is a 1 followed by 120 zeros. This discrepancy is so vast, it has been called the worst theoretical prediction in physics. If vacuum energy truly had such magnitude, the universe would have blown itself apart instantly after the Big Bang. Clearly, something is missing in our understanding. Some physicists suspect that unknown symmetries might cancel out most of this energy, leaving behind only the faint residue we detect as dark energy. Others look to ideas like the multiverse, suggesting that different regions of reality might have different values for vacuum energy, and we simply inhabit one where the value allows galaxies to form. Despite the mismatch, the concept forces us to rethink the nature of space. The empty gaps between galaxies are not blank voids. They carry fields, fluctuations, and a faint energy that shapes the destiny of the cosmos. This realization leads us to a deeper layer of the story. If the vacuum can drive expansion today, could it have done so in the past? This question takes us back to the very first fractions of a second of the universe, long before the formation of stars or galaxies. It brings us to a theory known as inflation. When cosmologists study the early universe, they encounter puzzles that the standard Big Bang model alone cannot explain. One of the most striking is the horizon problem. When we measure the cosmic microwave background, the faint afterglow of the Big Bang, we see a nearly uniform temperature across the entire sky. No matter which direction we look, the temperature differs by only tiny fluctuations. This uniformity suggests that distant regions of the cosmos were once in contact, sharing energy and smoothing out differences. However, according to the standard timeline, those regions should have been too far apart to ever communicate. Light would not have had time to travel between them. How could areas separated by billions of light years have coordinated their temperatures so perfectly? Another puzzle is the flatness problem. The geometry of the universe appears to be perfectly flat, meaning parallel lines stay parallel. For this to happen, the density of the early universe must have been tuned to a precise critical value. Any tiny deviation at the beginning would have grown enormous over billions of years, causing the universe to either collapse or expand too quickly for structure to form. In the early 1980s, a solution was proposed that addressed these puzzles at once. The theory suggests that in the first instant after the Big Bang, fractions of a second into existence, the universe underwent a burst of exponential expansion called inflation. This was not just steady stretching, but a violent doubling in size, again and again in unimaginably short intervals. This expansion was driven by a high energy field, often called the inflaton field, which behaved similarly to the vacuum energy we discussed today, but with vastly greater power. Inflation solves the puzzles with striking elegance. By stretching space so rapidly, it smoothed out any irregularities, much like stretching a wrinkled sheet makes it flat. It also explains the uniform temperature. The entire visible universe grew from a tiny patch that was once small enough to be in thermal contact. Before those regions could drift apart, inflation seized them and flung them across vast distances, preserving their uniform temperature as a fossil record of that early connection. What makes inflation particularly powerful is that it connects the smallest scales of physics to the largest structures in the cosmos. Remember the quantum fluctuations, the virtual particles popping in and out of the vacuum? During inflation, space expanded so fast that these microscopic jitters were stretched into macroscopic ripples. They became density variations in the fabric of the universe. When inflation ended, these ripples remained. Over billions of years, gravity pulled matter into the denser spots, eventually forming the galaxies and galaxy clusters we see today. The detailed maps of the cosmic microwave background produced by satellites match the statistical patterns predicted by this process. The faint spots of heat and cold in that ancient light are the echoes of quantum fluctuations, magnified to astronomical proportions. In this view, the galaxies are not random accidents. They are the direct descendants of the vacuum's restlessness. Connecting inflation to dark energy reveals a kind of cosmic symmetry. The universe appears to be bookended by two periods of accelerated expansion. The first was inflation, brief, violent, and driven by a high-energy field that set the stage for everything. The second is happening now, gentle, persistent, and driven by the low-energy dark energy that will determine the future. Some physicists wonder if these two phenomena are related. Could the energy driving today's acceleration be a faded echo of the force that drove the Big Bang? Or are they two different expressions of how gravity and the quantum vacuum interact? It is worth pausing to reflect on the timescale. Inflation lasted perhaps a tiny fraction of a second, yet in that instant, the universe transformed from a subatomic speck to something vast. From then on, the expansion slowed to the pace we associate with the standard Big Bang, allowing matter to clump and stars to ignite. Only recently, in the last few billion years, has the gentle push of dark energy taken over, accelerating the cosmos once again. Thinking of nothingness as a source of power changes our relationship with the night sky. The dark spaces between stars are not merely empty distance. They are filled with fields that hold the memory of the universe's violent beginning and the engine of its accelerating future. The void is not a passive container. It is a participant. Every cubic centimeter of space, from the gaps between atoms in your body to the gulfs between galaxies, holds a potential energy that we are only just beginning to understand. As experiments become more precise, physicists look for subtle signals that might confirm this picture. They hunt for primordial gravitational waves, ripples in space-time created by the violence of inflation imprinted on the cosmic microwave background. Detecting them would be like finding a fingerprint left by the universe's birth. Until then, the story of the vacuum remains one of the most compelling frontiers in science. It reminds us that our eyes deceive us. We see matter as the dominant reality, but the universe is mostly made of space, and that space is far from nothing. It is the silent, invisible ruler of cosmic history. The calm cosmos of today is, in a sense, the echo of an even faster expansion long past. Inflation, though brief, set the stage for everything that followed. When people first began to ask what the universe was, they often meant its size, its boundaries, and its shape. These questions were not only philosophical but deeply human, born of the same curiosity that makes us wonder what lies beyond the horizon. With the tools of modern cosmology, the question of the universe's shape and its fate has become something we can explore with data as well as imagination. The shape of the universe is not about its visible contents alone. It is about the geometry of space itself. General relativity tells us that matter and energy curve space, just as a heavy object curves the surface of a trampoline. Depending on how much matter and energy the universe contains, space can take on different global forms. A universe with high density curves positively like the surface of a sphere. A universe with low density curves negatively like a saddle. And a universe with exactly the critical density is flat, stretching infinitely without curvature. Each possibility carries implications not only for geometry, but for destiny. For much of the 20th century, scientists debated which of these three cases applied. The evidence was elusive until the cosmic microwave background was mapped with precision. Observations from missions like WMAP and Planck showed that the universe is astonishingly close to flat. On the largest scales we can measure, space does not curve like a sphere or a saddle, but stretches straight. The balance of energy density is extremely close to critical. This result was striking because flatness implies a specific kind of early history, one naturally explained by inflation. But geometry is only half the story. The other half is fate. A flat universe could once have been imagined to coast forever, gradually slowing under gravity but never collapsing. Yet the discovery of dark energy changed that picture. Now, the future depends not just on the amount of matter, but on the properties of this mysterious energy that dominates expansion. If dark energy is a true cosmological constant, unchanging in strength, then the universe will accelerate forever. Galaxies, not gravitationally bound to us, will recede beyond our horizon. Their light will stretch so far, we will never see them again. Over trillions of years, the night sky will empty, leaving only the stars of our local group, eventually merging into a single galaxy. Beyond that, even those stars will burn out, leaving black holes and cold remnants in a universe that continues to expand endlessly. This vision is sometimes called the heat death, not because it ends in fire, but because all usable energy is dissipated, leaving nothing but uniform coldness. If dark energy is not constant, Other fates are possible. Suppose it weakens with time. Expansion could slow, perhaps even halt. Gravity might eventually gain the upper hand, drawing matter back together into collapse. The Big Crunch would be the mirror of the Big Bang, a final convergence of everything into a single dense state. In some speculative theories, such a collapse might bounce into a new expansion, creating cycles of universes. On the other hand, if dark energy grows stronger with time, the future becomes even more dramatic. Expansion would accelerate so rapidly that eventually it would overwhelm not only galaxies, but the structures within them. Stars, planets, even atoms could be torn apart in what is known as the Big Rip. Space itself would expand so violently that no force could resist it. Current evidence favors the constant scenario leading to eternal acceleration. But because dark energy is poorly understood, the door to alternatives remains open. The shape and fate of the universe are not separate. Geometry and destiny are entwined. The curves of space determine how matter moves, and the contents of space determine how geometry evolves. When we speak of dark energy, of matter, of curvature, we are really speaking of a single system, space-time and energy shaping each other endlessly. The question of fate is the question of shape extended into the future. Yet, to truly understand this future, we must distinguish between the invisible players driving it. The words dark matter and dark energy often appear together, almost as though they are two sides of the same coin. Both are unseen. Both are mysterious. Both shape the universe in ways we can measure but not directly observe. Yet despite their similar names, they are profoundly different. To confuse them is natural because their invisibility and their dark label make them sound alike. But when we take time to separate what each one means, we find that they act on very different scales and in very different ways. The story of dark matter begins with galaxies. In the 20th century, astronomers studying the rotation of spiral galaxies noticed something strange. The outer stars far from the center moved much faster than they should if only visible matter were holding them in place. According to the laws of physics, gravity from the luminous stars and gas should have been too weak to keep those outer stars in orbit at such high speeds. They should have drifted away into intergalactic space, but they did not. They held together, turning with the inner galaxy as though bound by an unseen glue. The same was found in clusters of galaxies. The mass visible in stars and gas was not enough to hold the clusters together against their high orbital speeds. More matter was needed. Gravitational lensing, the bending of light by mass, confirmed it. Light from distant galaxies was distorted by intervening clusters, revealing more mass than visible matter could provide. This was the evidence for dark matter, an unseen substance that outweighs ordinary matter several times over. It clumps, it clusters, it gravitates. It is matter in the truest sense, though invisible. Dark energy is different. It was discovered not in the behavior of galaxies, but in the global expansion of the universe. Instead of pulling things together, it pushes them apart. Instead of clumping, it remains smooth and uniform. Its effects are not local, shaping galaxies or clusters, but cosmic, shaping the fate of expansion itself. Where dark matter strengthens gravity's pull, dark energy weakens it, counteracting it on the larger scales. To put it simply, dark matter adds to gravity. Dark energy fights against it. Dark matter makes structures form. Dark energy tears them apart over cosmic time. They are not the same unknown thing with two names. They are two distinct mysteries, each inferred from different kinds of evidence. Another way to think about it is in terms of how they distribute. dark matter gathers, it collects in halos around galaxies, providing the invisible skeleton on which visible matter forms stars and planets. Without dark matter, galaxies as we know them could not exist. Dark energy does not gather. It does not form halos or filaments. Instead, it is spread evenly across all of space, like a background property of the universe itself. No region has more, no region has less. Its influence is felt not in local systems, but in the overall acceleration of cosmic expansion. The physical nature of each also differs in speculation. Dark matter is thought to be some kind of particle, perhaps beyond the standard model of physics. Candidates include WIMPs, weakly interacting, massive particles, or axions. Scientists hope to detect them directly in underground detectors or produce them in particle accelerators. The search is experimental, aiming to catch dark matter particles interacting faintly with ordinary matter. Dark energy, on the other hand, is not thought of as a particle in the same way. The simplest idea is that it is the cosmological constant, an intrinsic energy of empty space. More elaborate theories imagine it as a dynamic field, perhaps changing slowly over time. But unlike dark matter, there is no experiment yet designed that can scoop up a dark energy particle. Its evidence comes from measuring cosmic expansion itself. The scales of influence highlight the contrast even more. Dark matter explains the motions of stars within galaxies and the binding of galaxies within clusters. It acts on the scale of thousands to millions of light years. Dark energy explains the acceleration of expansion on the scale of billions of light years. Encompassing the universe as a whole, one is local, the other is global. One pulls together, the other pushes apart. In terms of the cosmic budget, they dominate together. Roughly 25% of the universe is dark matter. About 70% is dark energy. Only around 5% is ordinary matter. This means that everything we see, stars, planets, galaxies made of familiar atoms, is just a minority ingredient. The universe is shaped more by the unseen than by the seen. Yet, even in that unseen category, the roles are split. Dark matter sculpts the structures. Dark energy defines the expansion. It is worth noting how the naming has shaped perception. When dark matter was proposed, dark simply meant non-luminous, invisible to telescopes. When dark energy was introduced decades later, the word dark was borrowed to convey mystery and lack of understanding. The shared term makes them sound like siblings, when in fact, they may be more like distant strangers, both unknown, but unknown in different ways. Sometimes people imagine that dark matter and dark energy might be two aspects of the same deeper entity. While that possibility is not entirely excluded, the evidence so far suggests otherwise. Their behaviors are too distinct. If a unifying theory exists, it would need to explain why one clusters and one does not, why one pulls and one pushes. For now, it is simpler to treat them as separate mysteries. The search for dark matter has taken many forms. Physicists build detectors deep underground, hoping to see faint collisions. Astronomers map the distribution of galaxies to infer its role. Its presence is clear gravitationally, but its identity remains hidden. For dark energy, the search is about precision measurements of cosmic expansion to determine if it varies with time. So far, the evidence favors a constant force, but uncertainties remain. In a sense, dark matter feels closer to us. It gathers around galaxies, including our own Milky Way, forming an invisible halo in which we are immersed. Every star you see at night, every planet, every cloud of gas is orbiting not just within the visible galaxy, but within a much larger dark matter structure. we are surrounded by it, swimming in it, held together by it. Dark energy, by contrast, feels more distant, more abstract. It is everywhere equally, but we do not feel it locally. It shapes the universe's fate, but not the orbit of the Earth around the Sunday. These differences matter for how we think about the cosmos. Without dark matter, the galaxies and clusters we see would not exist. Without dark energy, the universe's expansion would not be accelerating. One is the architect of structure, the other the driver of destiny. They coexist, but their roles are distinct. What unites them is their reminder that most of reality is hidden. The visible world, so rich in detail to us, is only a fraction. Beneath it lies an invisible majority, shaping the universe in ways we can measure but not yet explain. Dark matter and dark energy are not interchangeable, but together they remind us how much lies beyond direct sight. The challenge for science is not only to distinguish them, but to uncover their nature. When we look at the night sky, we are not only seeing the light of stars, but also the effects of what we cannot see. The spiral arms of galaxies spin as they do because of halos of dark matter. The distances between galaxies grow as they do because of the push of dark energy. Two invisible forces, different in essence, both shaping the same cosmos. The differences between them are as important as their names, a reminder that the unseen has many forms, each with its own role in the unfolding universe. When scientists began to realize that the universe's expansion was not just slowing under gravity, but accelerating, they needed reliable tools to measure distances across unimaginable scales. Seeing galaxies move away is not enough. You must know how far they are and how fast they are moving to understand the relationship between distance and velocity. But measuring cosmic distances is one of the most difficult challenges in astronomy. You cannot stretch a ruler across the stars. You cannot pace off light years with steps. Instead, astronomers rely on methods that transform certain objects into natural measuring sticks and lamps, standard candles, and cosmic rulers. The term standard candle may sound poetic, but it refers to something quite practical. A candle in a room gives a familiar amount of light. If you know how bright it should appear up close, you can judge its distance by how dim it looks when farther away. In astronomy, a standard candle is any object whose intrinsic brightness is known. By comparing the actual brightness with the apparent brightness seen from Earth, the distance can be calculated. The challenge is to find cosmic objects bright enough and uniform enough to serve this role. For decades, one of the most important standard candles has been a special type of exploding star, the type Ia supernova. These supernovae occur when a white dwarf star, the remnant of a star that has exhausted its nuclear fuel, accumulates matter from a companion star. Once it reaches a critical mass, about 1.4 times the mass of the Sun, the white dwarf undergoes a runaway nuclear reaction, exploding with extraordinary brightness. Because the mass threshold is nearly the same each time, the explosion has a predictable luminosity. Type Ia supernovae shine with nearly uniform brightness, making them cosmic beacons visible across billions of light years. By the 1990s, astronomers were using these supernovae to map distances to faraway galaxies. When they compared the distances to the redshift, the stretching of light caused by expansion, they expected to see galaxies slowing down under gravity. Instead, the supernovae appeared dimmer than expected, as though they were farther away than they should be. The implication was that expansion was not slowing, but accelerating. This was the discovery that revealed dark energy. Without standard candles, it could not have been made. But standard candles are not limited to supernovae. Other examples exist, such as Cepheid variable stars, whose brightness pulsates with a regular period. These were the first major standard candles used by Edwin Hubble to measure distances beyond the Milky Way. Today, Cepheids still play a role in anchoring the cosmic distance ladder, though supernovae extend much farther. The idea of cosmic rulers takes a different approach. Instead of using brightness, it uses size. If you know the physical size of a feature in the universe and you measure how large it appears in the sky, you can calculate its distance by simple geometry. A familiar analogy is holding your hand at arm's length. You know the size of your hand. By how large it looks against the background, you can tell how far away it is. One of the most important cosmic rulers is something called baryon acoustic oscillations. In the early universe, before atoms formed, the cosmos was filled with a hot plasma of particles and radiation. Sound waves rippled through this plasma, compressing and rarefying matter at regular scales. When atoms formed and radiation decoupled, these ripples were frozen into the distribution of matter. Billions of years later, galaxies still trace those ripples. By measuring the preferred spacing of galaxies, astronomers can use it as a ruler across the cosmos. The scale of these oscillations is about 500 million light-years, providing a gigantic yardstick imprinted from the early universe. Like supernovae, baryon acoustic oscillations help map the expansion history. They give distances at different redshifts, providing an independent check on dark energy's effects. Together, standard candles and cosmic rulers form complementary methods. One is based on brightness, the other on size. One uses stellar explosions, the other uses the large-scale structure of the universe. By combining them, astronomers gain confidence in their measurements and reduce uncertainties. These techniques are not abstract. They require enormous effort, both in observation and in analysis. Detecting supernovae billions of light-years away involves monitoring thousands of galaxies, catching explosions that flare suddenly and fade. Surveys like the Sloan Digital Sky Survey and the Dark Energy Survey dedicate years to building catalogs of such events. Mapping baryon acoustic oscillations involves charting millions of galaxies, measuring their positions and redshifts with precision. Telescopes scan wide areas of the sky, building maps of cosmic structure on unprecedented scales. The importance of these measurements is not just in confirming acceleration, but in probing its details. Does dark energy remain constant over time, or does it evolve? Do the data fit the model of a cosmological constant, or do they hint at something dynamic? By comparing distance measurements across redshifts, astronomers look for signs of change. Standard candles and cosmic rulers are the primary tools for this task. It is remarkable how much can be inferred from light, a supernova's brightness, a galaxy's spacing. These subtle clues reveal the grandest truths about the universe's expansion. In the end, what these methods show is that the universe can be measured even when it cannot be touched. Expansion is not something we feel in our daily lives, yet with careful observation, we can chart it with remarkable precision. The acceleration discovered in the 1990s was shocking, but it was no accident. It was the fruit of decades of developing standard candles and cosmic rulers, of building confidence that distances and redshifts could be measured reliably. Without these methods, dark energy would remain hidden. With them, it stands revealed as the dominant force shaping the universe's destiny. When we look at the night sky with our eyes, we see stars, planets, and the faint band of the Milky Way. With a telescope, we see galaxies, clusters, and nebulae. But there is another layer of the cosmos, invisible to human sight, that surrounds us entirely. It is not made of stars or galaxies, but of radiation, the faint glow of the universe itself. When it was only a few 100,000 years old, this glow is called the cosmic microwave background, CMB, and within it are subtle ripples, variations in temperature so small they amount to only a few parts in 100,000. Yet these ripples hold some of the deepest clues about the origin, shape, and fate of the universe. The story of the cosmic microwave background begins in the hot early universe. After the Big Bang, the cosmos was a dense plasma of particles and photons, too hot for atoms to exist. Electrons and protons were free, scattering photons constantly. In this state, the universe was opaque because light could not travel far without being absorbed and re-emitted. As the universe expanded and cooled, it eventually reached a temperature where electrons could combine with protons to form neutral atoms. This process, called recombination, occurred about 380,000 years after the beginning. At that moment, photons were released to travel freely through space, no longer trapped in the plasma. Those photons are still with us today, stretched into microwaves by billions of years of expansion. They fill the sky in every direction, a faint but detectable background glow. At first, the background seemed almost perfectly uniform, the same in every direction. That uniformity itself was astonishing, suggesting that the early universe was extremely smooth. But cosmologists realized that if it were truly perfectly smooth, no structures would ever have formed. Galaxies, stars, and planets require seeds, tiny variations in density that gravity could amplify over time. For decades, scientists suspected that faint ripples must exist in the background, too subtle for early instruments to detect. In 1992, satellites finally revealed them. The data showed tiny fluctuations in temperature, just as predicted. Later missions, such as WMAP and Planck, mapped the background with ever greater precision, producing all-sky images of the ripples in exquisite detail. These patterns are not random noise. They are the fingerprints of physics from the earliest moments of the universe. The ripples arise from sound waves in the primordial plasma. Before recombination, matter and radiation were tightly coupled. Gravity tried to compress over dense regions, while radiation pressure pushed back. The result was oscillations, waves of compression and rarefaction, much like sound waves in air. These oscillations left imprints on the distribution of photons released at recombination. When we measure the ripples today, we are seeing the echoes of those ancient waves frozen into the cosmic microwave background. What makes these ripples so powerful as evidence is that they encode multiple aspects of cosmology at once. The scale of the oscillations tells us about the geometry of the universe. The relative heights of the peaks in the fluctuation spectrum reveal the densities of ordinary matter, dark matter, and radiation. The overall pattern provides insight into inflation, the rapid expansion that preceded the hot Big Bang. In short, the ripples are a cosmic Rosetta Stone, translating the physics of the early universe into observable data. One of the key results from analyzing the background is the determination that the universe is nearly flat. The size of the ripples projected across the sky matches what would be expected in a flat geometry. If space were curved like a sphere, the ripples would appear larger. If it were curved like a saddle, they would appear smaller. The observed pattern fits flatness with remarkable precision. The ripples also show the role of dark matter. Without dark matter, the oscillations would look very different. Ordinary matter interacts with radiation, but dark matter does not. It provides gravitational wells that deepen the oscillations without coupling to photons. The balance between the two leaves a distinct signature in the relative heights of the peaks. By fitting models to the data, scientists can measure the amount of dark matter, finding it to be about 5 times more abundant than ordinary matter. Dark energy, too, leaves its mark, though more subtly. The expansion rate of the universe affects the distance to the surface of last scattering, the shell from which the microwave background photons come. By measuring the angular scale of the ripples, cosmologists infer how fast the universe has expanded since then. Combining this with other data provides constraints on dark energy. While supernovae and baryon acoustic oscillations give direct evidence of acceleration, the microwave background provides the foundation on which those measurements are built. It is striking that such faint variations, differences in temperature of only microkelvins, can tell us so much. They require instruments of extraordinary sensitivity, cooled to near absolute zero, shielded from interference, pointed steadily at the sky for years. The payoff is immense. A snapshot of the universe when it was young, encoded with the physics of its contents and its shape. The images of the microwave background are sometimes described as the baby picture of the universe. In them, we see not galaxies or stars, but the seeds from which they grew. To look at those maps is to look back across nearly all of time to see the universe in its infancy. The ripples also provide a testing ground for theories beyond the standard model. Inflation, for example, predicts that fluctuations should be nearly scale invariant, meaning similar on large and small scales. The data confirm this, matching the predictions closely. In thinking about the microwave background, it is easy to forget how far the photons have traveled. Every patch of sky glows with radiation that has been journeying for over 13 billion years, almost since the beginning. Each photon we detect today has crossed expanding space, redshifted from visible light to microwaves, carrying information from a time when the universe was young and dense. To measure those photons is to connect with the earliest chapter of cosmic history we can observe. The discovery and mapping of the ripples transformed cosmology from speculation to precision science. Where once parameters like the density of matter or the curvature of space were uncertain by large margins, now they are known to a few percent. The microwave background provided the anchor, the reference against which other observations are calibrated. It is no exaggeration to say that modern cosmology rests on those faint ripples. And yet, as precise as the data are, mysteries remain. The microwave background answers some questions while sharpening others. It shows us the outline of the cosmos, but the substance of its driving forces remains elusive. Even so, to reflect on those ripples is to appreciate the universe's capacity to reveal itself through faint whispers. From tiny variations in a background glow, we learn about geometry, matter, energy, and the earliest moments of time. The cosmic microwave background, quiet and uniform to the casual eye, turns out to be a vast record of the universe's history, written in the language of temperature and fluctuation. When astronomers first realized that expansion was accelerating, the simplest explanation was to revive an old idea, the cosmological constant. An energy intrinsic to empty space could provide the necessary push. It fit the data well and matched the mathematics of general relativity. But simplicity does not mean finality. Scientists are rarely satisfied with one explanation, especially when it leaves deeper questions unanswered. Why should empty space have energy? Why should its value be what it is, neither crushingly large nor exactly zero? These puzzles open the door to alternative theories, each seeking to explain dark energy in a new way. One such idea is quintessence. Unlike the cosmological constant, which is fixed and unchanging, Quintessence imagines a dynamic field that evolves over time. This field permeates space, much like the Higgs field or other scalar fields in physics. Its energy density can change as the field slowly rolls down a potential, much like a ball rolling down a gentle hill. Depending on the shape of that hill, quintessence could mimic a constant for a while, then drift, weaken, or even strengthen. In this way, quintessence offers a more flexible explanation. It connects dark energy to familiar ideas in particle physics, where fields rolling in potentials are common, from inflation in the early universe to mechanisms of symmetry breaking. Extending that concept to dark energy feels natural, yet challenges remain. The field must be incredibly light, with an energy scale far below what is common in physics. It must be nearly uniform across space, resisting clumping, and it must evolve slowly enough to resemble a constant over billions of years, yet not so slowly as to be indistinguishable. The behavior of quintessence is often described in terms of its equation of state, the ratio of pressure to energy density. For a cosmological constant, this ratio is exactly -1. For quintessence, it can vary, lying somewhere above -1, shifting as the field evolves. Measuring this ratio precisely is one of the goals of modern cosmology. If observations ever reveal a departure from -1, it would be strong evidence against a true constant and in favor of a dynamic field. But speculation does not stop there. Beyond quintessence lie even more exotic possibilities, sometimes called phantom energy. This leads to one of the most unsettling scenarios for the future of the cosmos, the Big Rip. To understand this fate, imagine dark energy not as a fixed background, but as something that grows stronger over time. In phantom energy models, the equation of state is less than -1. That means the pressure is even more negative than a cosmological constant. The result is that the energy density grows as the universe expands, rather than thinning out or staying the same. In such a universe, the repulsive force would eventually overwhelm every other force in nature. The progression would be dramatic. First, distant galaxies would accelerate away so rapidly that they would slip beyond the cosmic horizon, disappearing from view. Then, the Milky Way itself would lose its structure, its stars flung apart. Later, the solar system could unbind, planets drifting free from their star. Finally, on the most intimate scale, atoms themselves would be torn apart as the accelerating expansion rips even the electromagnetic glue that binds electrons to nuclei. This vision is not science fiction. It is a real extrapolation from certain equations of cosmology. While current observations do not favor such near-term scenarios, they do not completely rule out phantom energy. The Big Rip remains a valid, if extreme, hypothesis on the menu of cosmic futures. Another path of exploration looks not to new energy fields, but to modifications of gravity itself. General relativity has passed every test within the solar system, but perhaps on cosmic scales, it behaves differently. Maybe acceleration is not the result of an unseen energy, but of altered laws of motion for galaxies across expanding space. Theories such as FR, gravity, or brain world models propose changes to Einstein's equations that could produce acceleration without invoking dark energy. These ideas are challenging to test because they must reproduce all the successes of relativity locally, while deviating only subtly on large scales. Still, they represent a serious line of inquiry, reminding us that our understanding of gravity might be incomplete. Then there is the multiverse, which enters the discussion through a different door. The puzzle of dark energy's value is not just that it is non-zero, but that it is so small, compared to theoretical expectations from quantum field theory. Why? One speculative answer is that there is no unique reason, but rather a landscape of possibilities. If there are many universes, each with different physical constants, then we find ourselves in one where dark energy is small enough to allow galaxies and life to form. In universes with larger values, expansion would be so fast that matter could never clump into stars. In universes with smaller or negative values, collapse might occur too soon. We exist in the universe, compatible with our existence, a selection effect known as the anthropic principle. This concept is controversial. It explains the value of dark energy not by deeper law, but by statistics across unseen realms. Some physicists accept this as a plausible answer, while others view it as unsatisfying since it may not be testable. Yet it remains a candidate, arising naturally in some versions of string theory and eternal inflation. If the cosmos is indeed part of a vast ensemble, then our dark energy is just one entry in a cosmic lottery. Speculation about the unknown also extends to potential links between dark energy and dark matter. Some theories treat them as coupled phenomena rather than independent. In such models, dark matter might slowly decay into dark energy, or the two might exchange energy through hidden interactions. These possibilities attempt to unify the two mysteries under a single framework, though evidence is scarce. Still, amid all these theories, quintessence, phantom energy, modified gravity, the multiverse, one fact anchors the discussion. Observations so far are consistent with a simple cosmological constant. The data do not demand the exotic alternatives. They allow for them, but they do not require them. For now, the constant remains the baseline model, a placeholder until evidence forces something else. The role of theory is to explore possibilities so that when new data arrive, we have frameworks ready to interpret them. The search for departures from a constant continues. Surveys of supernovae, galaxy clustering, and the cosmic microwave background aim to constrain the equation of state. If it is exactly -1, the constant stands. If it is slightly different, quintessence gains support. If it varies with redshift, dynamic fields, or modified gravity may be needed. The precision of future instruments may be enough to tip the scales. It is remarkable how such a small number, the ratio of pressure to energy density, can hold such weight. The fate of the universe hangs on these subtle shifts. A difference of a few percent can determine whether the universe ends in a gentle fading or a violent tear. The big rip, the big crunch, or the heat death all depend on the precise nature of this invisible energy. Theories beyond the constant also remind us of the limits of current physics. General relativity and quantum field theory are pillars of modern science, yet they do not fit together seamlessly. Dark energy highlights that mismatch. Vacuum energy calculated from quantum fields overshoots reality by an almost absurd margin. Gravity does not explain why the constant is what it is. The variety of proposed solutions reflects the depth of the puzzle. These discussions often blur the line between physics and philosophy. The multiverse, especially, raises questions about what counts as science. If other universes are forever beyond observation, can they be part of physics? If the anthropic principle is the explanation, does that end the search for deeper law? The debate itself reflects the strangeness of dark energy, a phenomenon that resists simple categorization. Whether it is a constant vacuum energy, a rolling field of quintessence, a modified gravity law, or a multiverse selection effect, each offers a different vision of why the universe accelerates. Each has strengths, challenges, and implications for the future. Perhaps the truth is one of them, or a blend, or something not yet imagined. The unknown remains open, waiting for evidence to point the way. Until then, the Big Rip hovers as one of the dramatic options, a possibility born of mathematics and awaiting judgment by measurement. When astronomers realized that the universe is not just expanding but accelerating, it forced a rethinking of what that means for the galaxies scattered across cosmic space. Galaxies are not static islands. They are bound systems held together by gravity, yet they exist within a fabric of space that stretches. Acceleration changes the long-term relationships between galaxies, between clusters, and between what can remain visible to us. To imagine living in such a cosmos is to imagine what happens as expansion steadily pulls the grandest structures farther apart, turning the universe into a landscape of increasing isolation. Right now, the Milky Way is not alone. It belongs to a small group of galaxies known as the Local Group, which includes Andromeda, the Triangulum Galaxy, and dozens of dwarfs. Gravity binds these galaxies together strongly enough that the expansion of space cannot pull them apart. Instead, the Milky Way and Andromeda are on a collision course, destined to merge in a few billion years. On this scale, gravity wins. Expansion matters little within bound systems, but look farther out, beyond the Local Group, and the picture changes. Galaxies in the Virgo cluster, 50 million light-years away, are already receding from us due to the expansion of space. We can still see them, but their light is redshifted, stretched by expansion. With acceleration, their recession speeds increase, and in the very distant future, they will slip beyond our horizon, vanishing from view forever. The same fate awaits every galaxy not gravitationally bound to us. Over tens of billions of years, only the Local Group, by then merged into a single massive elliptical galaxy, will remain visible. Everything else will fade into darkness. This shrinking horizon is one of the most profound consequences of acceleration. The observable universe is not fixed. It evolves with time. Right now, we can see about 46 billion light-years in every direction, though the age of the universe is only 13.8 billion years. Expansion allows light from regions farther away to reach us, because those photons set out long ago when the universe was smaller. But acceleration means that fewer and fewer new regions will send light that can reach us in the future. The cosmic event horizon acts as a limit beyond which galaxies are lost forever, even if they exist and shine. For galaxies themselves, acceleration changes the long-term story of structure. In a decelerating universe, clusters could grow as galaxies fall together under gravity. But in an accelerating universe, growth slows and eventually halts. The tug of dark energy overwhelms the tendency of gravity to gather matter. Clusters freeze in their present form with little new material joining. Cosmic structure reaches a kind of stasis, not because gravity has stopped, but because the space between structures grows too fast for new mergers to occur. This has implications for the cosmic web, the great network of filaments and voids that spans the universe. Right now, the web is dynamic, with matter flowing along filaments into clusters. In the far future, that flow will stop. Filaments will no longer feed clusters. Galaxies within filaments will drift apart, losing contact with one another. The web will unravel, not in a dramatic tear, but in a slow isolation, as each bound region becomes an island in expanding space. For the inhabitants of galaxies in such a distant future, the sky will look very different. Today, telescopes reveal billions of galaxies stretching across cosmic time. In tens of billions of years, only the local galaxy will remain visible. Cosmology as we know it, would become impossible. No background of galaxies to measure redshifts, no cosmic microwave background to detect, no evidence of expansion. Astronomers of that era might conclude they live in a static, isolated universe. The clues we now use to infer acceleration would be gone, hidden beyond the horizon. The accelerating cosmos thus shapes not only physical reality, but also what is knowable. We live at a fortunate time when evidence of expansion is still accessible. Our era is uniquely privileged for cosmology, able to study the universe at large before acceleration erases its traces. Even within galaxies, acceleration plays a quiet role. While it does not unbind stars from galaxies or planets from stars, it sets the ultimate boundary conditions. Galaxies become isolated systems, evolving without fresh inflows of matter. Star formation slows as gas is used up, leading to aging populations of stars. The galaxy becomes a fading ember in an expanding void. Isolation scales upward from galaxies to clusters to superclusters, each severed from the rest by the relentless push of dark energy. It is natural to wonder if galaxies feel expansion locally, if space between stars is also stretching. The answer is subtle. Expansion is a property of the large-scale geometry of space, not of bound systems. Within a galaxy, gravity overwhelms expansion. Within atoms, electromagnetic forces dominate completely. Expansion is real, but it is not a stretching force applied locally. It is a change in the global metric of space-time, noticeable only when comparing objects across vast distances. Thinking about galaxies in an accelerating cosmos reveals the difference between local and global physics. Locally, galaxies remain secure. Globally, the distances between those islands grow, horizons shrink, and the universe's grand structures become solitary. The scale of change is not human, but cosmic, unfolding over billions of years. Yet its consequences are profound, reshaping the destiny of galaxies and the knowledge of observers within them. When we talk about the universe, one of the first challenges is simply making sense of time and distance on cosmic scales. Human senses are tuned to minutes and miles, yet when astronomers measure the universe, they speak of billions of years and billions of light years. In an accelerating cosmos, these measures carry even more meaning because they tell us not just what exists, but what we are capable of seeing and what we are forever cut off from. Light is our messenger, the only direct carrier of information across cosmic distances. When we look at a star, we are looking into the past. For the nearest star, the delay is 4 years. For distant galaxies, it is billions. Every view is a time machine, showing not what is, but what was. By stitching those snapshots together, astronomers reconstruct cosmic history. The universe becomes not just a place, but a timeline mapped onto space. Yet there are limits. Because the universe has a finite age, there is a maximum distance light could have traveled since the beginning. That defines the observable universe. Its radius today is about 46 billion light years. Anything beyond that horizon is forever invisible to us. Expansion sets a hard boundary around what can be known. Acceleration makes this boundary even stricter. In an accelerating universe, there is an event horizon, similar in concept to a black hole's horizon. Beyond a certain distance, even light emitted today will never reach us because space expands too quickly. Galaxies already beyond that horizon are gone from our future sky, no matter how long we wait. This is a striking consequence of dark energy. Not only does it push galaxies apart faster, it limits the flow of information. The universe becomes divided into regions that can never communicate, isolated bubbles defined by horizons. Even within our horizon, distance plays tricks. The light from a galaxy we see at redshift 2 has been traveling for 10 billion years, but that galaxy is not 10 billion light years away today. Because the universe expanded during the journey, its present distance is far greater. Astronomers distinguish between look-back time and proper distance because, in a dynamic universe, distance is not a simple concept. The stretching of light itself encodes expansion. As photons travel through expanding space, their wavelengths lengthen, shifting toward the red. This red shift is how we measure cosmic distances. Yet beyond redshift lies darkness. The cosmic microwave background marks the limit of what we can see with light. Before that epoch, the universe was opaque plasma. To see earlier requires different messengers, like gravitational waves. For now, the microwave background is our visual wall. Time and distance converge there in a snapshot of the universe when it was only 380,000 years old. Acceleration also changes how we think about future visibility. Galaxies we see today at high redshift may one day vanish. Their light reaches us now, but as expansion speeds up, new light they emit will never arrive. We are catching glimpses during a temporary window. Future observers billions of years from now will not have that chance. The accelerating cosmos is erasing evidence as it goes, inexorably trimming the accessible universe. This limit is not just a curiosity for astronomers. It is a profound statement about knowledge. The universe is not infinite to us in practice. It is bounded, finite, constrained by horizons that expansion defines. We can measure, infer, and imagine beyond, but we cannot observe. Our knowledge of the cosmos is shaped by what light can reach us, and dark energy dictates how much of that light survives the journey. It is worth pausing on how fragile this connection is. A photon emitted billions of years ago, traveling across space, stretched and weakened, still arrives in our telescope. If expansion had been faster, that photon might never have made it. If acceleration increases in the future, fewer such photons will survive. Every speck of light we gather is a triumph against distance and time. The limits of what we can see also mean the limits of what we can test. Physics thrives on observation, but horizons cut us off. We cannot check whether the laws of physics hold beyond our bubble. We cannot measure whether dark energy behaves the same in regions forever unreachable. We extrapolate, we assume uniformity, but ultimately, our theories are tested only within the bounds of what light delivers. Dark energy, by accelerating expansion, narrows those bounds, making the unknown larger. For galaxies, horizons mean eventual disappearance. For us, horizons mean eventual ignorance. The two are linked. The fading of galaxies from the sky is the fading of information. Cosmology is a science of light, and light obeys the geometry of space. As that geometry bends to acceleration, our science inherits the limits. Living with those limits does not make the universe less rich. It makes it more precious. The fact that we can see the cosmic microwave background at all is extraordinary. The fact that we can measure supernovae at billions of light years while they are still visible is fortune. Future observers will not have that fortune. Their horizons will be narrower, their evidence slimmer. In that sense, our age is not just early in cosmic history. It is uniquely well placed for cosmology. Time and distance, the twin coordinates of astronomy, reveal not just where things are, but whether we can ever know them. In an accelerating universe, those coordinates converge on a humbling truth. The cosmos is larger than what is visible, and expansion hides more than it reveals. As we measure galaxies, map redshifts, and trace the faint background radiation, we are sketching not just what the universe is, but what part of it we are allowed to see. The rest lies beyond the horizon, waiting forever unseen. We, for this brief era, enjoy a window wide enough to glimpse the universe in its fullness before dark energy pulls the curtain across. The universe is expanding, and the more we learn about it, the more the idea of nothingness becomes complicated. Once, it was easy to picture nothing as a void, an empty backdrop against which stars and galaxies arrange themselves. But the discovery of dark energy unsettled that simplicity. If space itself has energy, then emptiness is not empty. If expansion accelerates because the vacuum pushes outward, then even nothing has properties. The very stage on which the universe plays is part of the story, not a passive backdrop. With that realization, old philosophical questions take on new forms. When people spoke of nothing in the past, they meant absence. No air, no matter, no light, a silence without substance. But physics teaches that the vacuum is not truly bare. Quantum field theory describes space as a restless sea of fluctuations, particles appearing and disappearing in fleeting moments, fields permeating every region. What we call nothing is, in fact, a rich arena filled with potential and activity. Even if invisible, dark energy magnifies this point. If the expansion of the universe is driven by the energy of empty space, then the very concept of void becomes paradoxical. Nothing is doing something. Nothing has weight. Nothing shapes the cosmos. This perspective raises questions not only for science but for meaning. If the universe expands forever, fueled by vacuum energy, does the idea of nothingness vanish? Or is nothing simply redefined as the smooth, featureless field that drives acceleration? In philosophy, nothing has long been treated as a boundary concept, the opposite of being, the absence of reality. In physics, nothing has become a participant in reality itself. The two conceptions seem at odds, but perhaps they are converging. Consider what happens as galaxies drift away beyond horizons. The sky thins, stars burn out, black holes evaporate. In such a future, what remains? Space filled with dark energy, gently expanding, cold and silent. To an observer, that may feel like nothing. Yet by the laws of physics, it is not. It is an energy-filled vacuum with negative pressure, still shaping expansion. The universe does not fade into absence. It fades into a different kind of presence, one without structure, but with a force that never ceases. Philosophers once debated whether nothing could ever exist. Could there ever be a true void, a state without matter or form? Modern cosmology suggests the answer is no. Even stripped of galaxies, stripped of stars, stripped of particles, the vacuum itself persists. Fields are not optional. They are the fabric of existence. Nothing, in the strict sense, is unattainable. There is always something, even if that something is invisible and abstract. Dark energy makes this unavoidable because it ensures that the universe cannot be imagined as a bare container. The container has energy. The stage has power. When cosmologists say the universe came from nothing, they often mean a quantum vacuum. That is not nothing in the philosophical sense. It is a structured field with laws capable of fluctuations. The accelerating universe forces us to revise even our most basic categories. Nothing is not the opposite of something. Nothing is another kind of something, subtle and pervasive. This realization may echo in other areas of thought. If nothing can expand, then absence is no longer sterile. If nothing has energy, then potential is built into the fabric of reality. The boundary between being and non-being blurs. Philosophers spoke of the void as terrifying, a source of existential dread. Science now presents it as dynamic, perhaps even necessary. Without vacuum energy, there would be no acceleration, no unfolding of the universe as we know it. As we follow the story of dark energy across the vast stretches of time and space, there comes a point when the details blur into something quieter. The galaxies that once filled the night sky drift away, their light redshifted until it fades into darkness. The background glow of the early universe grows colder and weaker, stretched into invisibility. The great clusters stop growing, filaments unravel, and what once was a connected cosmos becomes a scattering of isolated islands, each sealed off by horizons. It is a future without drama, but filled with inevitability, the slow unfolding of expansion until the universe itself becomes a place of stillness. In such a setting, stars continue their work for as long as they can. They burn hydrogen into helium, helium into heavier elements, until their fuel runs out. The remnants, white dwarfs, neutron stars, black holes linger far longer than their luminous parents. Over trillions of years, even those remnants change. White dwarfs cool until they are invisible embers. Black holes dominate for longer, swallowing matter, merging, radiating faint traces of energy until they too evaporate through Hawking radiation. The cycle of stars, once the drama of the universe, eventually ends. Planets share that fate in their own quiet way, bound to stars while they shine, stripped of heat when they fade. Planets become frozen spheres wandering in darkness. The grand stage of cosmic evolution narrows down to empty rocks, blackened remnants, and the soft pressure of dark energy pushing everything farther apart. Acceleration ensures that this process is not simply a decline, but an irreversible drift. It is a universe that does not collapse back on itself, but instead stretches into ever greater emptiness. And though emptiness is the word we use, it is not truly void. It is filled with dark energy, the quiet background that continues its work without end. For an observer living in such a distant future, the night sky would be unrecognizable. Where we see billions of galaxies, they would see only one their own. Beyond that, nothing. The idea of cosmology, of studying the universe at large, would be impossible. There would be no evidence of expansion, no cosmic microwave background, no distant galaxies to trace. The universe would appear static, eternal, an island of stars surrounded by perfect darkness. The story of expansion would be hidden, written in light that never reached them. That is why this moment in cosmic history is so unusual. We live at a time when the evidence of dark energy is still visible, when galaxies and clusters can still be measured, when the faint background from the beginning of time can still be detected. We live in an era when horizons have not yet closed in too tightly. To future observers, that record will be gone. To us, it is a gift, a brief window into the fullness of the universe before acceleration narrows the view. Thinking about the long future of stars and planets under dark energy is not only an exercise in physics, but also a reflection on what it means to exist in such a vast timeline. Human life is fleeting compared to galaxies, and galaxies are fleeting compared to the expansion of space. Yet in that fleetingness lies perspective. The atoms in our bodies were forged in stars that lived and died billions of years ago. The light that reaches our eyes tonight may have traveled longer than humanity has existed. We are part of this vast process, not apart from it. The gentle ending implied by dark energy is not destruction, but dispersion. Instead of a fiery collapse or a violent tear, it is a fading into stillness. The energy that drives expansion does not roar, it whispers. It works not in sudden catastrophe, but in patient separation. Galaxies drift, stars fade, matter cools, horizons close. The result is not chaos, but quiet, not violence, but solitude. It is an ending, but one that comes softly, with no sudden moment of finality. To rest in the vastness of such a vision is to accept that the universe does not promise permanence. It evolves, it changes, it moves toward states that are very different from the one we know. Yet in those changes is beauty, the beauty of understanding, of glimpsing the shape of a story larger than ourselves. Dark energy ensures that the universe will not return to what it was, but it also ensures that we live in a moment when that truth can be seen, when horizons are still open, when galaxies still shine together. It may be that the deepest lesson of dark energy is not about the future, but about perspective. To know that space itself carries energy, that emptiness is not empty, that the universe accelerates on scales beyond comprehension, is to feel the smallness of our place. Yet that smallness is not insignificance. It is connection. We are made of matter shaped by these same laws, part of the same expansion, observers capable of noticing and of telling the story. The universe may end in quiet dispersion, but in the meantime, it gives rise to awareness, to questions, to meaning. And so, the gentle ending is not only the future of stars and galaxies, it is also the calm realization that our place within the universe is fleeting but real, that the vastness does not erase us. It frames us. As the cosmos rests in acceleration, we too can rest in the knowledge that we have seen it, that we have asked about it, that we have lived within it for a brief, luminous moment. Thank you for drifting through this journey tonight. We have wandered from galaxies to horizons, from the silence of stars to the strange whisper of dark energy, and now the universe feels a little larger, yet perhaps a little closer, to wherever you are, beneath your own stretch of sky. The same expansion carries on, patient and unhurried. If you found comfort in this exploration, you are welcome to return again whenever you would like to fall asleep with science at your side. You can follow along, subscribe, or simply let the next story play while you rest. There will always be more questions waiting among the stars. For now, it is enough to close your eyes, to let the thoughts drift like galaxies into the quiet distance, and to know that you are part of the same vastness we have been speaking about. Sleep well, and may the universe keep you gently